All right, it's 11:15. We'll get started. Welcome to MATSE 202. My name is Mike Hickner. I'm a professor of material science and engineering. And my building and lab is Steitel on the other side of campus. It's the one with the little round porch, if you don't know where it is. When conditions improve, feel free to come on over and check out the labs in Steitel. It's a really awesome building to work in. You can see what my graduate students do, making polymers and doing experiments on electrochemical systems and other types of polymer membranes. But we'll save the visits for a little while. So the first thing off is that make sure you can access the Canvas page. If there's something wrong with your registration, or if there's some funky thing, or you just added the class last night, wait a day. But if you can't access the Canvas page by Wednesday, give me a shout. I'll just add you and then everything will be fine. But Canvas is going to be really important because all the assignments will be put in through Canvas, scanned, and then uploaded. So make sure you have printing facilities or a tablet or something so I can see your handwriting. That's really important for this class, and make sure you can upload those documents. We'll do that for homework, so you'll have some practice, but exams will be on Canvas. So exams will be some multiple choice questions, probably like 20 multiple choice questions. And then there will be a written part as well that you need to print, fill out, scan, and upload. That won't count against your time, so you won't be super rushed on the written part. But Canvas will have a time limit for your exam for the multiple choice, and then the written part will be some extra time as long as everyone's reasonable about that. So anyway, get familiar with Canvas. Yes. Yeah, so you don't have to print it out. Just put your name, MATSE 202, exam number 1, question number 1, write down the answer. Yeah. So you don't necessarily need to print it out if you're looking at the screen, etc. That's fine. As long as I can see handwritten solutions, that's really important. Yes.
I would assume it would be the same thing with the tablet, except it's already in file form.
Yep. Tablet is fine as long as it's handwritten. So just no digital answers. Although for homework 0, it's a typed assignment, so you can just type it in however you want. That's fine. Homework 0 is the exception. Everything else is handwritten. Any other questions? All right. So you can check out all this general information on Canvas. And so this is the home page where all the information is with the modules. And especially important are the homeworks. So you have a homework due on Friday. It's really easy. Check it out. I will activate homework 1 today too, so you can look at homework 1. That will be due next Friday, just so you can see what the information is going to be like. But homeworks will be due every Friday, except if we have an exam or something like that. There's nothing to give a homework on. And so make sure you're looking at those due dates for homeworks. Also, we have something called pre-lecture assignments, or PLAs. They show up, I can't point there. Oh, maybe I can. They show up in our homepage. And so they're due before class. And so they're called pre-lecture assignments. So PLA 1 is due on January 13th. Then you come to class on the 14th. I have a feeling that January 16th PLA is wrong because we don't have class on MLK Day next Monday. And so let me tweak that a little bit. But you want to be looking at these PLAs because they will count for a percentage of your grade. They're to warm you up. They're to get you in the mood for the material. Make sure you're thinking about the material before you come to class. And so the PLAs are to make sure that you just stay in the game with the material and that you're ready to ask good questions in class and think about the material. Yes. PLAs are not timed, but they will stop, I think, at midnight the day before class. So don't start the PLA at 11:55. They don't take that long, maybe half an hour, maybe less, but every day before you come to class, on Sunday, on Tuesday, on Thursday, be like, I've got MATSE 202 tomorrow. Maybe I have a PLA to do. And so I don't know exactly how Canvas works from the student side of things. Maybe you can set a reminder, maybe something, but you should be thinking about this class regularly, especially since homeworks are due on Friday. Make sure that you're thinking about the homework throughout the week. We're going to cover some material on Monday and Wednesday, maybe even Friday, that will lead you to the homework, but you can finish up the homework on Friday afternoon and turn it in before the weekend so you don't have it hanging over your head on the weekend. Although if you want to print the next homework and look at it over the weekend, that's fine. But during lecture and during office hours, that's a really great time to ask questions to get ready to turn in the homeworks. You know, I'm not going to answer a lot of questions on Friday night about the homework. And so that's a bad time to start thinking about it. A good time to start thinking about it is you do the PLA on Sunday night, print off the homework, take a look at it and say, okay, this is what I need to think about this week. And then you have that homework assignment with you and you start checking down, okay, I got that, I got that, I got that. And then throughout the week, you'll be able to get the homework done. And so again, make sure that you prepare and make sure that you're thinking about this class ahead of time, and I will help you as best I can, because if you email me at 10 p.m. on Friday night, I'm not going to see that until after the homework's due. Any questions so far? All right, and I am an amateur Canvas user, and so if something doesn't look right on Canvas, just give me a shout and say, I think you goofed something up. And I'll take a look at it, because you just never know. All right, so that's really important. And then if you look at the announcements, and I have a million announcements because I have them saved. So we'll scroll down to the very first announcement. Everyone should have gotten this today, and you got one yesterday from me. And so if you click on this thing, you get to the OneDrive, and this is where all the notes are. And so this is going to be really important because the grading guide is in here. The syllabus is in here that we'll talk for a second about. And then section 1 is where we are right now. These are all the PowerPoint notes for the class. And when I write on the notes up here, they show up on the OneDrive. So you can look at the notes before class and sort of figure out where we're headed. And then after class, you'll be able to go back and say, oh, Hickner was writing something on that slide. What was it? It should be right back in there. So there aren't sort of 2 sets of notes. It's just one living document. Let's see. First off, let's go to the syllabus first. There's my contact info. Please email me through Canvas. I will see it on Canvas. There's no guarantee I'll see it if you just email me directly. Class times, that's great. Prereqs, really important for this class is the organic prereq. If you haven't had it, you can let me know. Otherwise, I'll teach you what you need to know. But if you've never seen organic chemistry before, you're going to have to be on top of that. All right, and here's the schedule. This is probably pretty solid. We'll see. But homework due dates are all alliterated for you right here. So make sure you put those in your calendar or whatever, but in general, we'll have a homework due every Friday. And all the exams are set. So February 2nd, we're having an exam. End of February, we're having an exam. March, we're having an exam. We have an exam 4. We have a significant number of exams because I think having more exams is good because it gives you a chance to show me what you know. There's a lot of material in this class, and we drop one exam. So each exam is worth 20% of your grade. So we have four midterms, but we drop one. Everyone has a bad day. Everyone gets sick. The material of the class doesn't resonate with everyone, excuse me, in terms of a section. And so you will be allowed to drop your lowest score for one of the 4 midterms. The final is also 20%. Everyone has to take the final, and the final counts. You can't drop the final. And so make sure that that's all set. Let's see. You must turn in all assignments. Homeworks can't be skipped. You might miss a PLA, that's fine, that will impact your grade, but you can't skip any homeworks, they're important. If you skip too many assignments, you will get an incomplete in the class, and that's not good. And so make sure you handle that. I'm probably going to give you a little bit longer on the exams. They're not 70 minutes, maybe 90 minutes, maybe 80 minutes. They'll be on Canvas. You won't have to be in the room to take them. And so just make sure that you think about where your happy place is going to be for taking the exam. It will be open on that day, but you can take it anytime, except I don't know what Canvas does when you go overtime, like past midnight or something like that. So start it before then, but you'll be able to take it anytime during that day. And once you start it, the clock will be running and then you have to finish it and that's it. So you won't have to take it during class time. It gives us some flexibility to work on that, but you do have to take it on the day unless you have an excused absence. Excused absences, of course, are always okay. All right. Grading policy, it's the usual, and then all the other syllabus stuff. So make sure you take care of your academic integrity. It's fine to work in groups, but it's not fine to copy. Make sure you keep up on your attendance or let me know. Excused absences are absolutely fine. We'll handle those. If there are any barriers to you accessing the material in this course, let me know. We have plenty of tools to handle that. And so I'm totally flexible in terms of making sure that everyone has the same educational opportunity to learn the material, because I love polymers. And so I want to make sure everyone has a chance to do well in this course. All right, great, great. Okay, that's all fine. There was one other thing that I wanted to say and I totally, oh, okay. The book, let me go back to my Canvas page here. So you notice in the syllabus, there's section numbers for the book. And the book is right here. It's an online ebook. You don't have to buy any books. Oh, come on. Oh, it's not here. Sorry. Okay, this textbook material. So this is an ebook online. It's really great. If you're going to be a polymer professional, it would be okay to buy this book, but maybe some of you don't know. Yeah, but this is a really nice book. It's got good examples. It's got practice problems. It's got really nice explanations. It's got a lot of background material. It's easy to follow. And so, you know, my notes will be important because that in general will be what I test you on. So I'm not going to test you on anything that we don't talk about. So the notes form the important part of the course, but the book is a really great resource. So don't forget about this. It's easy to read. It's a nice book. It's online. You can just click around on it and find what you're looking for. So this is really great, especially for vocab, especially for, I forgot what that term is. I forgot what that concept is. You can look in the index and turn right to the page for this book. And all the sections, again, are in the syllabus. And so it will really give you that extra information for this class. So I highly recommend making sure you keep in touch with this book as you move throughout the class. All right. I'm going to try and post all the videos either on YouTube or on the media gallery. We'll see if the videos are any good. I'm trying to record it on Zoom. We'll see. I'm not sure. All right, so back to the OneDrive. Great, we saw the syllabus. Here's the grading guide, just to make sure you know what's going on. So make sure you're, oh, well, there's no Zoom. Sorry about that. I can't edit it, so I'll fix that. But make sure that you're turning everything in. And for the resident section, we do have an online section, and I'll handle those folks separately. But in the resident section, you want to get above 75% on the PLAs, that's full credit, and above 75% on the clicker questions, that gives you above full credit. So if you miss a class, you know, if forget a PLA, you know, if it's just, I forgot one or two things, it's not a big deal. There aren't any makeups on PLAs because I have to go back in and open them up, and that's a hassle. If you miss one class, it's no problem. If you miss 10 classes, you know, that's getting to be harder unless they're excused absences, and we'll do our best to fill in on the excused absences. But you need to be here and you need to engage with the material in the class, and you'll be super successful. There's lots of people that do well in this class. This is an introductory class in polymers. And so there's lots of people, including you, all out there that can do great in this class and get the grade you want. But the ones and twosy points are not going to matter that much. It's really being here for the full experience, then you'll get the grade you want. All right. So we're going to be in section 1 for a while until exam 1. And so we're just going to follow the notes 1, 2, 3, 4, even though I might call them lectures. They're not called lectures. We'll just march through the PowerPoint slides. Are there any questions? Yes.
Do you curve exams at all?
Nope, no curves. There are 10 people out there that are going to get hundreds in this class. I guarantee you, you have a lot of smart colleagues. You have a lot of people, a lot of classmates that will be high achievers. This is an introductory class, and so it's not meant to weed you out. It's meant to bring you in to the field of polymers. So there's absolutely no curve on anything. Yeah, there'll be people that get hundreds, no problem. Yes?
Are the PLAs only available the day before? Can you do that sooner?
I think they open up a couple days before, and so in general, like the PLA that's due on Friday will probably open on Wednesday, and so you'll have a couple of days. It's not going to be a rush, and I just have to go in there and communicate with Canvas in the appropriate way. So it won't be a rush to get the PLAs done, as long as you remember after dinner, before the lecture, the day before you come to lecture, you just check out the PLAs. You'll be able to get it. Yeah.
PLA 1 is available at 4 p.m.
There you go. Yeah. So the Canvas tells you when it's coming up, you know, I think. All right, let me go to this view so I can actually write on the notes.
Honestly, at first whenever I saw PLA, I thought it was like the filament for like a 3D printer.
That's right. I like that. See, polymer joke right off the bat. That's good. You get an A for the day. But yeah, PLA is polylactide or polylactic acid, and it's used for 3D printing. Often we actually won't learn that much about PLA in this class. That's in the next polymer class. But you know, I'm liking this, talking about polymers right away. Great. Okay, that's all the information. Again, send me email through the course Canvas page. I promise you I will see it there. All right, so in this class, we really want to develop an understanding of polymer molecules, what they are, what they look like, what their chemistry is, and how all of those molecular properties lead to physical properties. So everyone in this room has experience with polymers, right? Those seats are made out of polymers. This carpet's made out of polymers. This screen is a polymer. We have a lot of polymers in our cell phone cases, et cetera, et cetera. So polymer should not be a strange term. However, polymers have been around for a while, and there's a really interesting body of science developed around polymers to understand how they work. They're a little bit different than other types of materials that you might have come in contact with. And we know that because glass or window glass or steel or ceramic coffee cup, we sort of know or have an intrinsic idea that those types of materials are different than polymers. And so this class is going to be why are polymers different and what gives them their properties. So we'll talk about all this stuff. And what's really important, and I know that everyone loves this, and so make sure that you are familiar with the organic chemistry concepts that we're going to talk about. So Chem 202 or 210 is a prereq for the course. Some of you have gotten that way, but not all of you. But I'm going to expect that you're able to sort of be comfortable with these organic chemistry concepts, especially nomenclature and drawing structures. I mean, we're not going to do SN2. We're not going to do E1 mechanism. Yeah, we're not going to do mechanistic stuff. Don't worry about that. But the first part of organic in terms of nomenclature, you know, when I say hexane, there should be a hexane molecule that goes off in your head and you're like, okay, hex 6, it's an alkane, it's saturated. Okay, I know what that is. I know what carbon looks like in hexane. And so it's going to be relatively simple, but you're still going to have to work with the molecules. You're going to have to push a couple arrows, but in an easy way, but no mechanistic stuff. And the other important polymers is that there are long chains of molecules. We're going to talk a lot about this. And so polymer has poly in it as part of its root, which means there's lots of things. And it turns out that polymers are really long, stringy molecules. And that's what makes them special. Other types of materials are not put together in the same way. So we're going to talk about chemistry of polymers. We're going to talk about this chain idea or macro molecules, big molecules, and then we're going to talk about how both of those things influence polymer properties. Because eventually, at the end of this course, you want to be able to say, okay, you know, if I need a certain polymer to do this, this is kind of the polymer I'm looking for. Or if I'm looking at a polymer on a piece of paper, this is sort of my idea of what the properties could be. And so we want to get you familiar with how the molecular chemistry is connected to how we experience polymers in everyday life. All right, this is just, you can read that if you want. And so we're going to talk a little bit about synthesis, because in order to really understand polymer molecules, we need to know how they're made. We need to know how they're put together. And the synthesis that we do is going to be pretty easy, but you're still going to have to focus on it. So again, no mechanistic, not a lot of stereochemistry, not a lot of that, but there will be some arrow pushing. You know, what does a double bond mean and how do you work with that? What's a single bond mean? How do you work with that? Things like that. And then once we talk about synthesis, what is the macromolecular structure? So what does that chain look like? It turns out there's a bunch of different polymer chains. And so we're going to talk about polymer chains a lot. What are their properties? And then we turn the circle. What aspects of the chemistry and structure affect the properties? And then eventually you can connect this loop and say, okay, if I want a different polymer, this is what I would do. All right, and we'll talk a lot about functions and applications because polymers are super useful. In some cases, they're a big problem, and we'll talk about that as well, because in order to solve plastic pollution, you need to know something about plastics. And so as a polymer scientist, I say, you know, part of environmental plastic pollution is my problem, but you also need me to help fix it. And so if we learn about how polymer molecules work, we have a chance to do something really important. I think these links are updated. You can check them out. But, you know, ebook, lecture videos to be determined, online material. It turns out there's a website for this class as well that really mirrors the book. I suggest you use the book, but you're welcome to check out this website as well. That's what the online folks will be using to guide them. Okay, that's the book. Sarah and Harrison are the TAs. They will really focus on the grading. It's going to be me that interfaces with you because there's not lots of students in this course. And so they'll be busy doing the grading. You might want to communicate with them if you want, although they won't answer your emails probably. They'll just send them to me. And so I'm your gateway to this class. And so make sure you just ask me the question first. Harrison and Sarah have other things to do. All right. Oh, make sure you at least print the syllabus schedule or have that syllabus schedule in a place that you can easily access it, because a lot of the questions that I get about the class can be answered through the syllabus. I mean, I don't mind telling you it's in the syllabus, but that's the answer you'll get from me if you ask me a question that's covered in the syllabus. There are lots of questions that aren't covered in the syllabus, so ask away. I'm available, but I'm not being a jerk if I say it's in the syllabus. I'm directing you to read the syllabus because things that are important to you for the class are in that syllabus. And so you should be pretty familiar with that document. Okay, Zoom office hours until things change. We're going to be all Zoom. Monday and Tuesday, 3 to 4, and Thursday, 1 to 2. Now, I know that everyone's got lots of classes and labs and everything else. If you have another suggestion for office hours, I'm listening. So not after 5 p.m., not before 9 a.m. You know, I'm a business hours person. And so I'll take suggestions during the business day to do office hours. You're welcome to make an appointment with me. That's no problem. Just keep it during working hours. And every office hour will be at this link. I'll be there. You'll be there. We'll do whatever we need. Make sure to share your screen, or you can point your camera at your paper. I'll be able to write stuff down and help you through it. If we're having a horrible time, a good time to answer questions or to do a quickie office hours is either right before or right after class. Oftentimes when we start class, I'll say, are there any questions from last time or any questions on the homework? Boom, that's a great time to ask a question. Because if you have a question, especially concerning the homework or something you don't get from last lecture, everyone can hear it. So, you know, make sure you take advantage of before and after class time too. I'll have extra office hours for exams, critical things. If I have to miss an office hours, I'll have a makeup office hours, but we'll try and go with this unless people rebel and everyone says they're totally booked for these hours. So just let me know. Talked about grades, eye clickers, we're gonna use them. Sorry, otherwise it's top hat, but eye clickers, maybe I'm old school, but I like them. I identify with them. So we'll try eye clickers and see how it goes. All right. So you already saw the syllabus, and so make sure you're familiar with our schedule. And you see that we're going to have a few exams talking about molecular structure and how to build molecular structures and really thinking about that material and engaging with polymers through what they look like in terms of building up the molecules. And so this is just our order of topics right here, but we're going to work on this for a while because this is how you get into polymer science. And everything that you're going to need for your future polymer career is going to be in this section. We're also going to talk about some advanced concepts. And so this is a little bit shorter of a section because these concepts are harder. Florey-Huggins is tricky because it's polymer thermodynamics, and I know you all like that, but this gets you really oriented to advanced things in polymer science. And for the people that really want to take up polymers as a focus, this section will be important. All right. And then finally, we're going to talk about some cool things that polymers do. We're going to talk about 3D printing. We're going to talk about polymer electronics, because polymers can conduct electricity. We're going to talk about lithography, how to make Pentium chips, and things like that. And so we're going to have a section on that as well. All right, any questions, any comments so far? Okay, again, I'm willing to take comments by email or before or after class, that's fine. And so, you know, we'll just get into the swing of things this week. So polymers, like I said, is a common word, or should be a common word to people that are getting a bachelor's degree in science and engineering. And basically it's a big molecule or a macromolecule. So poly means a lot of them, mer means one unit, or macromolecule means the same thing. Macro means big, molecule means a molecule. And so polymers are big molecules. So you can visualize it as a ball of string, a plate of spaghetti. It turns out that polymers are moving. And so maybe a pile of worms that are moving is a little bit more apt, except worms are too short. They're not high aspect ratio enough to be polymers. And so what's interesting about this ball of string is that if I try and reach in there and pull out one string from a ball that looks like this, what generally happens? Yes. You pull a lot of strings, right? If you're a knitter or if you have a really messy sewing basket and you try and pull out their toolbox and try and pull out that one string, a lot of other polymers come with it, or a lot of other strings come with it. And that's exactly what happens with polymer materials. If you try and pull out a little piece of a polymer, a lot of things are dragged along with it because all of those molecules are tangled up with each other. And we call those entanglements. And so I'm going to write down that vocab word and you can think about that before our class next time. And so this is a key vocab word. If you forget what entanglements mean, you can Google it. Turns out that Google and Wikipedia know some facts about polymers. I mean, I wouldn't go too far on the web, but there will be some new vocab words that you need to become familiar with. And so entanglements is one of those. And all entanglements are is polymer molecules are wrapped around each other. You try and pull on one molecule and the rest of the polymer comes with it. Because what's one property that sort of jumps into your head when you think of polymers? What's one, here's a polymer. What goes off in your brain? Yes.
Flexible.
Flexible. That's right. What's another property? Maybe, yeah. They're soft. That's a good one. And if it's soft, it's usually what's a little like a racquetball or something. It's what property? Elastic, or maybe rubbery or gooey. That rubberiness and gooiness and softness and elasticity is all because of these entanglements in these long molecules. Metals aren't soft. They're not elastic in the macromolecular way, even though they can undergo elastic deformation, but you can't really experience that as a human. Our skin is elastic. Our skin is soft. Our skin is a polymer. And so it's really those unique entanglements and unique macromolecular structure that gives polymers their unique properties. Good. So if we want to think about a polymer from an organic chemistry point of view, or at least a chain point of view, this is a chain. And we can conceptualize this as a polyethylene chain. And sorry, this is a ridiculous chemical structure. I don't know why it keeps showing up poorly. But if we take ethylene, which is a small organic molecule, right? Eth means two, and ene means it's unsaturated. So we call this molecule ethylene. Make sure you know that. That should be, a piece of cake for you, as long as you refresh your memory. And if we make polyethylene, you see that double bond in the center of ethylene. There are 4 electrons in there, right? Because the straight line in organic chemistry means 2 electrons. And so if we take 1 electron and push it this way, 1 electron and push it this way, we have a single bond now because we've gotten rid of one of those double bonds. Carbon, hydrogen, nothing's happened with those. Then we need to figure out where those electrons went. And we don't write them as dots. We write them as a single line with a parenthesis through it, which means 1 electron, and then we put the N there for repeating. So we go from ethylene molecule to polyethylene polymer. Now that's a little tricky unless you stare at it and turn it around. And what we did was we have C, double bond C, C. I don't know why that keeps coming up. So I'm just going to draw the carbons of ethylene, and we took an electron and put it that way. We took an electron and put it that way. Half arrows, right, means 1 electron. And if we do that over and over and over, N in this case is 1, 2, 3, 4 molecules, so N would equal 4. We've connected 4 ethylenes in this polyethylene type structure. So you can draw that out. I think that's going to be a homework problem on homework number 1 that's due in a week and a half or something like that. But this starts the organic chemistry part of how to treat these organic molecules, because most polymers are made out of carbon, and so organic chemistry is going to be important. All right, you'll get to practice that again. And so this now is a 200 mer, or there's 200 little dots, and so a dot is ethylene. So if we connect 200, we get a chain that looks like this, and that molecular weight is going to be 5,600 grams per mole. And we're going to talk about molecular weights in a second, but 5,600 grams per mole is a big molecular weight, right? Did you have any molecular weights or chemical structures that were that heavy in organic chemistry or in Gen Chem? No, it's huge. It's a macro molecule, right? And so I'll show you all the accounting that it takes to figure out what the molecular weight of a polymer is. But this idea of a chain and high molecular weight in macromolecules is the important part of what we want to learn at the outset to figure out what polymers are doing. Molecular weights can be high. So this is 1 million molecular weight for polyethylene. There's something called ultra high molecular weight polyethylene that they put in hip implants, and that's like 10 million grams per mole. So molecular weight will be important as we go forward. The other thing that's really interesting about these long chains is that we can look at the aspect ratio. So aspect ratio is usually the length divided by the width, or the length over the height, or the long dimension divided by the short dimension, because usually aspect ratio is a number greater than 1, unless we have some sort of frame of reference. But the aspect ratio of polymers is humongous. So if we scale up this polymer, we say this molecule is 1/4 inch in diameter, or its width scales to 1/4 inch, then the length would be 1/2 mile long. And so the aspect ratio of most polymer chains is longer than threads. You know, you could take a thread maybe from here to the hub, and that's about the aspect ratio of a polymer chain. Because molecules are very small, right? We can get an idea of the width of this molecule by the carbon-hydrogen bond distance times 2, right? That looks like the width. We can figure all that out. We can take into account the size of hydrogen atom if we want. So we can get the width by adding up all those molecular parameters. Then we can get the length by summing all these carbon-carbon bonds. And so the aspect ratio of polymers is really, really big, much bigger than worms. We're talking threads that are all stuck together and you're never going to get them untangled. So that's an interesting thing to think about. Polymers just aren't long and skinny. They're really, really, really long and really, really, really skinny. They have tremendous aspect ratios. All right, any questions? All right, let's keep going. I think we still have, we still got 10 minutes, tons of time. All right, polymer or polymer properties that are the most important or most easy to conceptualize on the first day of MATSE 202 is this idea called viscoelasticity. So visco derives from viscous. Elasticity derives from elastic. And it turns out that elasticity and viscosity are two opposite properties. Viscosity is just the resistance to flow, and elasticity is the bounce back of a molecule or of a material. And so for an elastic solid or a viscoelastic solid, when the time is short, sorry, T is not capital T, that's temperature. When the time is short, polymers behave like elastic materials. So we could take the idea of a piece of silly putty, if you know what that is. So silly putty, you can mold it, it's like clay, you can roll it up in a ball. And it turns out if you bounce that silly putty on the desk, it bounces just like a rubber ball. Or at short times during that bounce, it behaves elastically. At long times, if you leave silly putty on the couch or on the carpet, It slowly oozes down and you'll never get it out of your couch. It behaves like a liquid. So this is like a viscous liquid. And so this time dependence of properties is really important for polymers. So there's time dependent. Whoop. Time-dependent properties. And so the material looks different depending on the time scale over which you measure it. If you take that silly putty and snap it really fast, it'll break, just like a hard material. But if you stretch that silly putty slowly, it just sort of oozes down just like a liquid. And so we'll learn about the time dependence of polymers. And so this is just giving you an idea of all the different types of materials. So if you're not in material science or you haven't studied a lot of materials, this gives you a map for things that we consider hard materials and things that are softer materials. Glass is a really interesting one. We can talk about what that means. It turns out that that glass in that window back there is flowing just like silly putty. It's just flowing really, 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 really slowly. And so we don't get to see it at human timescales at the temperatures that we experience most window glass. So that's interesting. It turns out there's polymer glasses as well, like this cover right here for this overhead projector. This is a glassy polymer. It feels hard. But if I take this thing and I stretch it really slowly, it's going to behave like a liquid. It's just we have to wait for a really long time, or we have to heat the temperature up to make the molecules move faster. All right, let's keep going.
Is that like related to the glass transition point?
Perfect. So glass transition is a temperature. So we call it the glass transition temperature because when we're above the glass transition temperature, we have a viscous liquid. When we're below the glass transition temperature, we have a glass. And we're going to talk about TG either next lecture or the lecture after, because it's the physical property, the glass transition temperature, that determines whether a polymer is hard or soft as we use it in the world. And so if we want to make a coffee cup out of polymers, in general, we're going to need a high glass transition temperature polymer because we want that polymer to be hard. We want it to be a cup, especially when we pour hot liquid in it. So we use polystyrene, the polymer of styrofoam, which has a glass transition temperature of about 105 degrees Celsius. So that polymer doesn't flow when we put hot coffee in it. However, one second. However, for car tires, we use polyisoprene or we use natural rubber that has a glass transition temperature of about -100 C. Because even in the winter time, we still want polymers to be a little bit gooey or a little bit flexible. And it turns out the car tires are flexible to give us grip on the road. And so we use a low TG polymer because we want that polymer to work at low temperatures and not be glassy. So we'll talk about TG in a sec, but talking about glasses versus viscous liquids, it's the glass transition temperature that defines the border between the two. Yes.
So we're talking about glasses, but the arrow, it says gases.
No, gases, sorry.
So is gas
That's
in
funny.
liquid form, or is it
No, gases are not that soft.
Okay.
Sorry. Let's call this glasses. That's hilarious. I think that is a misprint because a gas is not that interesting of a material, although the physicists might disagree. Sorry, glasses. Let's do that. Any other questions or comments? All right. So there's lots of polymers around. That's why they're important. MATSE 202 is a great class. That's why polymers are important. So that's what we're going to talk about. Polymers can also be used to address lots of grand challenges that society and scientists and engineers are facing today. And so making solar energy economical, I'll show you some polymers that are used to make solar cells. That's really important. All the solar cells out there right now have a polymer encapsulant on them. That's really important. And so engineer better medicines. There's lots of polymers that are used in biology. Think of controlled release drugs, think of IV bags. Lots of our masks right now are polymers as well. And so polymers play a big role in health. Reverse osmosis membranes for clean water are the #1 technology for purifying salt water for human consumption. And so polymers just play a huge role in all of these challenges. And here too, so whether you're interested in grand challenges for engineering or the UN Sustainable Development Goals, there's lots of polymers out there. The drawback of polymers is that they come from places that look like this. And so polymers are generally derived from petrochemical sources or oil. And so this is an issue. There are lots of natural polymers out there, but the world has really gotten used to synthetic polymers. You know, we've gotten used to polymers to make cell phone cases, and we've gotten used to car tires that perform well. Those are highly refined natural polymers or synthetic polymers. You know, we don't use a lot of natural polymers other than cellulose or some other niche applications. And so this is a big issue because if we make polymers here, a lot of polymers have ended up here in the Pacific garbage patch or as plastic pollution. And so we need to come up with ways to mitigate this and to come up with the next generation of polymers. Most polymers that we use today were invented in the 1950s, 60s, and 70s when we had the technology revolution after World War II, and we're still using those polymers. And those polymers really weren't designed with the environment in mind. So it's time to think about other types of polymers, how we can use biodegradable polymers, and how to figure out how to make the polymers for the 21st century. So like I said, polymers are ultimately useful, and this is why we use a lot of polymers now. So even if we don't use plastic bags at the grocery store, you know, we still want to make sure that we have prosthetics. We still want to make sure that we have medical devices. We still want to make sure that we have artificial hearts. One of the polymers in this artificial heart was invented at Penn State, as a matter of fact. And so polymers are really useful. Polymers are also used in the digital age. So for a process called photolithography. So this is photolithography. There's something in 3D printing called stereolithography, which is just photolithography in 3 dimensions. But in order to make all these chips, you need polymers. And so companies like Intel and others use lots and lots of polymer science in order to do this photolithography. And the people that invented photolithography, this was invented in Rochester, New York, and at Cornell University. They're still alive and they still go to polymer meetings. And so some of these advanced uses of polymers are not that old. It's a really interesting area to work in because some of the folks that built the field, you can go talk to at a meeting. All right. And so there's lots of common polymers in clothing. There's whether you're interested in silicones, which is a polymer. Of course, silicon is an element. Cotton is a polymer. Spandex, if you know what that is. So this is synthetic rubber that's in lots of different clothing. That's a type of polymer. And here's cellulose again. Polymers are used in contact lenses. And so you're not old enough to remember when we had hard contact lenses, but they were horrible and hard to use and they caused lots of problems. Now every contact lens is a soft contact lens. And it was a really big deal in polymer science to invent these types of polymers to be used in soft contact lenses. Let's see. Let me just go to one more slide here. So polymers have sort of been around for a long time, but they only knew about polymer chains since the 1920s. So Staudinger was awarded the Nobel Prize for coming up with the idea that polymers are chains. And now we've got polymer art and antiques. So Bakelite antiques are really interesting. We have modern art that's made out of polymers that people are trying to think about preserving. And finally, one of the people who invented Kevlar worked for DuPont, is a famous scientist, was born in New Quay. And so Stephanie Kowalik is a really cool person. You can go meet her at American Chemical Society meeting. So polymers are out there, they're important, they're all around, and we're going to learn about them this semester. All right, see you on Wednesday.